Hi students, today we will start one of the subject for the GATE examination, that is digital electronics. And let us coming to the introduction for this subject. The main application of digital electronics is in the topic called digital circuits. Suppose if we consider any digital circuits, the main function of digital circuits is it has to process the given input signal. So here the inputs for these digital circuits like this, let us say some applying input, and it is also having some output. And here the input for the digital circuits generally is in the form of some digital part. Similarly, the output is also digital, but whatever the signals available in our physical form, those are not in the digital form, they are in analog format. The original signal is in the form of analog form. So for that we need some transducer, let us say some ADC. So ADC is converting the analog signal to digital, and then that digital part, that digital input is applied to digital circuits. Similarly, whatever the output that is coming from these digital circuits, again we need to convert using DAC to the analog format. So our original signal is in the form of analog, so we have to convert the analog to digital, and we have to process that signal, digital signal, using some digital circuits. And again at last, again we may convert, sometimes we require in the digital format or we may require in the analog format. If it is required in the analog format, we need to convert this digital to again analog using this DAC. And the main functioning of digital circuits is it has to process the signal. So what are the examples for this digital circuits means? It may be some microprocessor or microcontroller or any digital signal processor. This is called some highest level, high level digital circuits. The digital signal processor called as high level digital circuits. Now, but in our subject, we do not, we should not deal with some high level. Very lowest level we are studying, or we need to study the very lowest level, and that is what are the topics that we are studying in the lowest level means logic gates or multiplexer, some demultiplexer, or some arithmetic circuits. All this comes under combinational arithmetic circuits. And in addition to this, we will also study some sequential circuits. Those are called flip-flops, registers, counters, and some memories part also. Memories. And in addition to this lowest level, further, even lowest level, we need to study even very basic. That means the diodes. How these logic gates are implemented using some diodes and transistors. Okay. Next. So here we are saying that we are applying some input to the digital circuits. We are applying some input to the digital circuits. And what is the purpose of studying this subject? We are applying some input and we are getting some output. Now, if this input, the input is having some larger expressions, the input is having larger expressions. The input may contain some very more number of variables, and it is having some large expression. So here in this subject, initially we will learn how to minimize. We will learn minimizing the logical expressions. After minimizing the logical expressions, and those logical expressions are those that input is applied to the digital circuits, and it will process the signal. So here the main purpose of studying subject is we are minimizing the logical expression in the initial part, in the starting of the syllabus. So let us move on to the first topic called Boolean algebra. Boolean algebra. So the main purpose of studying this Boolean algebra is, and this Boolean algebra is used for logical expression minimization. Logical expression minimization. The Boolean algebra is used for minimization of logical expression. So up to where we can use means, and this is used for this Boolean algebra is used for minimizing logical expressions when the variables are when the number of variables are very less. When the number of variables are very less, that means some 0 and 1. When the number of variables are very less and the output may be 0 or 1, and the output may be 0 or 1. And actually this Boolean algebra was introduced by George Boole in the 1857, I think 57 or 54. Okay, and this was implemented for minimizing the logical expression whenever the number of variables are very less. That means we have to use Boolean algebra only when the number of variables are very less, and this cannot be applied for when the input expression is having larger number of variables. We cannot apply this Boolean algebra. Then what we have to do? Then K-map or corner map is used when the number of variables are more. When the number of variables are we can take from 2. When the number of variables are 2, 3 and 4 and 5, you can use the K-map. And the output may be, what are the output you may get is, it may be 0 or 1, or sometimes you can also getting the output X, that is don't care. That don't care means it is not bother whether it is 0 or 1. That is the function of K-map. And still if the number of variables are more than 5, then we have to use Quine-McCluskey method. Quine-McCluskey method when the number of variables are more than 5. So all these methods, Boolean algebra or K-map or Quine-McCluskey method, all these are using for when use it for minimizing the logical expressions. So based on the number of variables, we have to use a particular method. So let us the basic theorem. Let us see the basic theorems first. The basic theorems are using not, and, or. These are the basic theorems in this Boolean algebra. Not means if the variable is a, its complement is represented with a bar. So if the input is 0, then its complement is 1. If a is 1, its complement is 0, opposite. That is a not theorem. And coming to the AND theorem, let us see the truth table for that. Let us say like this: a dot a, whenever you are performing AND operation between a and a, you will get a. And if you perform AND operation between a dot 1, which is equal to a, and similarly a dot 0 is 0. And when you are performing AND operation between the variable and its complement, a dot a bar is also 0. And similarly OR theorem or OR operation, a plus a is equal to a, and very important, a plus 1 is equal to 1. And this is very important, because while minimizing several logical expressions, you came across many number of variables plus 1, and it is default, the output is 1. And a plus 0 is equal to a, and sum of the variable and the complement of the variable is equal to 1. This one, a plus a bar is equal to 1 and a dot a bar is equal to 0. Many times we will use these conditions. And let us simplify one expression. Let us simplify one of the simple expression. Simplify a plus ab plus ab bar. So which is equal to, in these expressions, a is common, so we can take a dot b plus b bar. So already using this OR theorem, b plus b bar is equal to 1. A dot 1 is equal to a, and this one is called as uniting or unity theorem. Next, let us simplify one more thing. A plus ab. A plus ab, from these two terms we can take a common. We can write it as 1 plus b. So 1 plus anything, it is simply 1. So a dot 1 is equal to a, and this one is called as absorption part or absorption theorem. Why? Because one of the variable is absorbed by using this 1 plus b part. And let us move to let us see one of the question. What is the minimum number of logic gates? The question is, what is the minimum number of NAND gates are required? What is the minimum number of NAND gates required to implement the given expression AB bar plus ABC bar plus ABC? So first, let us simplify this expression using our known theorems. AB bar, from the second and third term, AB is common, so AB plus C bar. We can write it as AB bar plus C bar is equal to 1. So AB, from these two terms, A is common, A dot B plus B bar, which is equal to A. So from the given question, in the given expression, we are getting is equal to A. We are getting the given expression is equal to A. That means the question is, what is the minimum number of NAND gates? So after simplifying the given expression, you are getting the given expression y is equal to A. So if the input is having some variables A, B and C, and we need to implement the given expression, so y is equal to A. So y is equal to A means there is no need of any NAND gates for implementing this expression. So the input is a simple wire is required. A single wire is required, is sufficient for implementing the given expression. So in the question, it may be some confusion. That means they are confusing like this by giving the a different question like this: A is equal to 2, B is equal to 4, 5, and the last option is 0. That means while preparing the question, they want to confuse the confuse the student. So what is the minimum number of NAND gates required to implement the given expression means, first directly without minimizing this logical expression, they may implement and you may get some 5 or 4. But here, after giving the expression, first we need to minimize the given expression, and then the correct answer is 0. So I hope you understand this. Now the simple question is, why we are minimizing this logical expression, or what are the advantages of minimizing this logical expression? We will see in the next video. So I hope you understand this question. Thank you.